Okay, hello, we're going to get started. It's good that there's all this chatter. People are excited, people are fed well. We still have some people grabbing food, but I think we're going to get going. We have a very special physics club today. We have Dr. Eun-Joo who's going to talk to us about physics at Yale. This is going to be recorded as well for people, just so that you can tell all of your friends who weren't smart enough to be here, as you were here in your seats. Do we have anyone else with 2 PhDs here today? Anybody 2 PhDs? No. No, it's an unusual and wonderful background, really phenomenal. You read about these people in books, but don't think you're going to meet one of them. Dr. Ahn's PhD in astronomy and astrophysics from the University of Chicago was in 2006. She worked on one of my favorite experiments, the Pierre Auger experiment. I remember hearing about it and how you had to deal with systematic uncertainties due to cattle interacting with the detectors, which I thought was amazing. But she was diving into cosmic rays and the makeup of cosmic rays. She then was working on developing a hadronic interaction model of cosmic ray content as a postdoc at Fermilab. And you can see already when you Google her, which I have been doing recently, some hints of her interest in history really early on. When she was at Fermilab in around 2010, 2011, there was a collection of someone's papers and writings. She was already getting small grants to try to do something with this material and thinking as a historian. She went on to get her PhD in history from UC Santa Barbara in 2023, her second PhD in a very different discipline. And she was looking at how astronomers of Mount Wilson Observatory interacted with their environments during the early 20th century. We got her to Yale thanks to Reina Mariama's Asian Americans in STEM initiative, and she inherited that class that you were teaching with Mary Lou. And now she is doing an amazing job teaching what I think is one of the hardest classes. She's teaching our Introductory Physics for Life Sciences course, formerly 170, now 1700. So I am thrilled that you're here. We're lucky to have you here at Yale in lots of contexts. As you'll see, one of the things she's been doing while she's been here is learning and studying the history of physics at Yale. So take it away.
Thank you, Sarah. And can you hear me? Yes. Yeah. Okay. Yeah. Thank you, Sarah, so much for that. Yeah. Flattering introduction. Yes. So I will be telling a story of the physics at Yale. It's not the definitive. It's not a comprehensive. It's not inclusive, because I'll be keeping you for weeks if I do that. So when I first came to Yale 2 years ago, I saw, sorry, how do I work this? Okay, yeah. So I saw the Wright Laboratory with its portal and the Sloan Physics Laboratory. And I really naively thought, okay, so I was given a tour that there's the portal, which was the old accelerator. So I thought everything was as is, except the old accelerator was taken out. And I thought this was the physics building since the founding of Yale, and it has always been occupied, full of activity in research, teaching, administration since centuries ago when Yale was founded. I wasn't even sure when Yale was founded. And little by little, I started hearing more, learning more about this place, and I realized how wrong my preconception of both places were. So Sarah gave me a flattering introduction, but I just wanted to tell a bit more about myself as how I turned from an astrophysicist to a historian of science. So yes, I worked on particle astrophysics, mostly phenomenology, on hadronic interaction and the most energetic particles in space, ultra-energy cosmic rays. And the experiment I was part of, is called the Pierre Auger Observatory. It's located in the foothills of the Andes in Argentina. And as Sarah mentioned, some of the systematics the collaboration has to deal with is cattle hitting water tanks. Because it's a hybrid detector where one is, we have about, when I was part of it, I would say we. There's about 1,600 water Cherenkov tanks that's getting the muon imprints on ground. And then there's 4 sets of ultraviolet telescopes that looks at air fluorescence signals caused by the air shower in dark night sky. So yes, cattle do hit this. Birds love to sit on top of the antenna, and then they, have droppings on the solar panel. This decreases the efficiency of the solar panels, and that's also something people have to look into. And the contribution I was most proud of is when we study composition of the highest energy particles, there are not that many. The flux drops like crazy, e to the minus 2 or 2.7. So when you go above 10 to the 19 electron volts, the number of events really start dropping. And my proudest contribution was introducing something other than proton and iron. Because in high energy cosmic rays, there's proton, iron. And we systematically introduced something like helium family and nitrogen family. So when I was doing the Piero J collaboration, it was truly international. The Americans were a minority. And it was intergenerational. And I got to see different contributions people made. I mean, they say physics is universal, but the set of toolkits people had were different. We talked different mathematical or physics language to solve a problem. The procedures were slightly different, but in the end, it was a collaboration. So that really got me wondering more and more of why are we doing physics this way? So and that question became more pressing. So I transitioned to history of science. And when I talk to historians, they really veto the idea of doing it as a hobby, but they say, if I'm serious, I should go back to grad school and get proper training. I mean, if you think the other way, if a historian came to the physics department and says, hey, I'm interested in physics, can I just work on it? You wouldn't really say yes to that. So my first research topic was on a place called Mount Wilson Observatory. It was founded more than a century ago. It's located near Pasadena in Southern California. And some of you might be familiar with this photograph. So I was introduced to this photograph that shows Albert Einstein, theorist, together with Edwin Hubble, observational astronomer, looking at a telescope. It was a placeless, timeless photograph, usually used as to put in some humor into cosmology lectures. And when I was looking through various materials for my research, I came across this photograph again and was shocked because it had a place and time, and the photograph was cropped. This person was cropped out of the photographs that I encountered in astrophysical lectures, and it turned out that he was actually a very important person. He was the director of the observatory, and this isn't a photograph, it's a film clip made by Frank Capra, the film director. And people talk here. So Hubble is absolutely silent, he just smokes his pipe. Einstein does all the nodding, and Walter Adams does all the talking, describing the observatory. So that gave a different spin. And I really looked into how is scientific knowledge made? Who are the participants of scientific knowledge? So we do need contributions from people like Einstein and Hubble, as well as other less remembered, powerful astronomers like Adams. But, we also have these participants. So these are women astronomers whose names were forgotten. They are recorded but less remembered. And they are also doing scientific knowledge making. So this was taken during a lunch break or coffee break of a conference. And we all know that we do physics while we discuss with others. It's not just solving problems, but when we attend collaboration meetings or conferences, talking to your peers is an important part of doing physics. So that's what they're doing. And my work included showcasing these people who do science as well. So when I came to Yale, I was able to do my dormant research on Asian American physicists. So I was interested in how immigrant scientists, Asian Americans or those from Europe, how did they shape scientific practice and the type of physics we do? So we all know, accept that science is, like when we do science, it's a collaboration, we interact with others. But can the participants, the composition of these participants also affect what kind of physics we do and the knowledge we make? So I'm curious about that. And as an Asian American scientist myself, I was also curious how this small number of people really shaped like the perception and bias towards Asian Americans, like the model minority myth. So my work on Benjamin Lee, who was a theoretical particle physicist, was published a few months ago on Physics Today. So as I was doing physics research and historical research, I realized there are similarities in both. So history is evidence-based storytelling of the past. We need to rely on evidence. It's not just making things up. And we collect data as well. But instead of making experiments or observing through telescopes, we go to the archives, libraries, or we go to the place itself, or we meet people and we collect data there. And we analyze those data. So some can be looking through correspondences. It can also be going through newspapers, magazine articles. It can also be looking at like actual artifacts like microscopes. It can also be talking and interviewing people. So we have to tell a story that doesn't contradict the evidences. So in that way, I find there are similarities between physics and history. And when I was here, I got the opportunity to study more about the history of physics at Yale, and oh boy, I learned so much from it, and I'm still learning it, so what I'm telling is an incomplete story. And I got to realize that when I first jumped into this, I thought, okay, there must have been a physics department at Yale, and we can just start from there. And then it turned out that Yale was founded in 1701, and there was no physics department. Actually, there was no physics then. It was something else called natural philosophy. So studying the development of physics at Yale provided a way to study how physics developed in the United States, and to realize that it wasn't like sudden jumps. It wasn't individuals making a revolutionary change, but it was a continuous change that reflected the college and the individual's interaction with the social and natural surroundings. So Yale College was founded in 1701, and some of you may know already that it was a rebel college that was rebelling against Harvard for being too liberal. So conservative people escaped to Connecticut to find a college that's going to train men to take positions in church and state to create theocracy. And natural philosophy, which was the study of natural phenomena, natural bodies, that can be where like physics grew out of. That was considered a very important part of the curriculum because studying nature revealed how God ordered the universe. And the division between religion and science is something artificial and that came much later. There was no contradiction for people who were very religious studying natural philosophy or science. So right from the beginning, natural philosophy was very important. And it was 1701, and it was a time in Europe where a lot of new thoughts were coming into place. So in the early 1600s, British natural philosopher Francis Bacon was proposing we need to have a systematic way of understanding our world. So he proposed there should be empirical studies which were systematic. Others, like René Descartes, were also proposing this mechanical universe. So people were attuned and they were aware that we should be studying the nature with our eyes or doing experiments instead of relying on classical authorities. It should be systematic, it should be mathematized, and what else? It should be experimental. They should try things, and it should be as objective as possible. So it was under these ambiences that Isaac Newton published Principia in 1686, and it's like a few years later that Yale was founded. So the founders, the presidents, they were aware of how natural philosophy should be taught and its role. So they invested a fair amount of budget in buying books and instruments. So that included telescopes, microscopes, barometers, and it turned out that one of the earliest microscopes purchased by the college is still preserved at the Peabody Museum. So that is fascinating. So the presidents, the rectors, they knew the importance of natural philosophy. They bought the instruments. And one of the presidents even went far as to design a huge orrery, like the model of the solar system, that was 7 feet wide. And it's usually said that's the first orrery system in North America. That survived until the American Revolution, when it was burnt down, probably by the British. But there wasn't a lot of active teaching. It was just yes, it's important, we need to teach it. But it was like steady like that. And after the revolution, the Yale presidents and other important people thought, okay, this college should support liberal education, as in a sound grounding of the students in classics, which included science education. And they supported that, they defended that. They were against ditching the classical languages and literature. They said that is very important foundation. And in a report that defends the liberal education and their approach, they state the importance and the role of science, that in attending to the physical sciences, he becomes familiar with facts, with the process of induction and the variety of probable evidences. And the faculty and the presidents thought this was a vital part of liberal education. So they wanted to continue science education, and in 1802, they hired Benjamin Silliman Sr. as the professor of chemistry and natural history. So Silliman was interested mostly in mineralogy. So he went to, after his appointment, he went to Edinburgh, and he took lectures at the university, gained knowledge. He also used his personal acquaintance with other rich people to, get patronage, funding, to buy a large mineral collection for the university. And because Yale hired a professor to teach natural history and chemistry, they had to find a place for this person to teach and possibly do experiments. So the very first place that carried out experiments or lecturing in science was a tiny place called the Lyceum. So this is an old map of Yale. So this is the old campus. And what you see here, SM, is today's Connecticut Hall. If you go to old campus, you might see a smallish building in the center of the plaza, open space. So that's this building. Other buildings, they all got razed down. And next to the Connecticut Hall, there was a Lyceum. So this was Benjamin Silliman's first place to do lectures and experiments. And this is a description that Arthur Wright wrote about the place many decades later when he was writing about Silliman. So in 1802, the building known as the Lyceum was erected. In providing for the foundations, a deep excavation was made at the west end, which it was understood to furnish a place for the laboratory. The final result was remarkable. A room almost underground was finished above with groined arches and with so limited window space as to admit a mere glimmer of light, sufficient to make the darkness painfully visible. The depth was so great that when the lecturer stood upon the floor, his head was 6 feet below the surface of the ground. And he writes about some of the, like how Silliman was aghast at it and some of the improvements Silliman made. So anyway, in this place so greatly exposed to dampness that all iron articles rapidly rusted and chemical preparations capable of absorbing moisture deliquesced with discouraging facility, the chemical instruction was given for 15 years. So this was pretty typical of the universities or the colleges' reaction. They wanted science. They provided something to the minimal, and it was pretty inadequate. One had to really push for improvements. So after staying in this terrible Lyceum, which was underground nearly, for 15 years, Silliman finally got another place, and it's called the Old Laboratory. And this was initially the commons, or the cafeteria for the students, and the commons got another better place. So into this empty building, the science faculty, Silliman moved in. So it's here, the lab, and this is a colorized photograph of a black and white. So it looks quite pretty. But if you look at other photographs, it's the shabbiest building in this old campus. So Arthur Wright continues to give further descriptions of it about how lectures were taken and experiments. So the lecture place was a big improvement compared to the Lyceum. So they added a wing. The rising seats in this portion of the room were assigned to the ladies, large numbers of whom were constantly present at the lectures. So this was not a surprise and a surprise at the same time. Yes, so women did study science. Women attended colleges in an informal capacity. And they had a segregated section where they sat at lecture. But they were highly interested in chemistry lectures. So in fitting up the building, the seats from the old lecture room were transferred to the new one and continued to render service for many years. So I presume the old lecture room might have been the one at the Lyceum. They were very narrow, with high, nearly perpendicular backs, and are doubtless painfully remembered by the survivors of the many college generations who occupied them. In 1872, the lecture room was refitted in part, the old seats being replaced by others of better proportions and with slopes better accommodated to modern ideas of comfort and convenience. So the quest for better lecture chairs is not something modern. It happened in the past as well. And we continually quest for better seats, better tables, and desks. So that's the lecture portion. Wright also goes on to describe the improvements or changes made to carry out experimental work. So the chambers were converted into one room by removal of partitions and fitted up for optical work because Wright was interested in optics. He observed the zodiacal light. He would carry out spectroscopic observations of meteorites. So the walls, floor, and ceiling are blackened, windows provided with close-fitting shutters to render it completely dark at any time, and suitable arrangements provided for the introduction of light from the sun, the electric arc, or from other sources as may be desired. And some of us might remember from our high school or middle school or university chemistry class, 1850s, 60s was a big jump for spectroscopic studies when gratings, There were prisms, but gratings. And more discoveries were made, studies were done considering spectrums. So optics was one of the most interesting fields to be in, to study nature. So Wright was describing what was going on in terms of office buildings and lab space. And the more general picture of what was going on in the 1800s is, yes, there was liberal education that was emphasized by the faculty. And this enabled them to further push for higher studies. So Yale became the first university or college in the US to have this graduate department. It was called the Department of Philosophy and the Arts. So that was formed in 1847. So that didn't come out of the blue, but I believe that having a strong liberal education, rationale, and presence really gave the faculty this very good reason to push for further education. And at the same year, the Yale Scientific School was founded. And later it was named the Sheffield Scientific School due to its patron, Joseph Sheffield. So this came about, again, not out of the blue, but because non-academics, academics were realizing, yes, science is very useful. Not only do we get knowledge, but it's fueling industrialization. It's related to power, it's related to financial gain. So if we support development in science, we also get a return back. So more industrialization, more efficiency, more profit. And slavery in the US, the transatlantic slave trade, that was the backbone of supporting all these labors. So patronage for science increased in the 1800s, not only for the pure desire to gain more scientific knowledge, but also because it was linked to financial gain and power. So throughout all these, Yale College or the Yale Corporation supported science and physics teaching and research in the sense that they never stopped the faculty when they proposed something. They say, oh yes, it's a wonderful idea. But they didn't give a lot of financial monetary support. That was up to the faculty to find it. So like the Yale Scientific School, it was founded. Yale College fully supported it. They didn't give a lot of funding, and it was flailing and about to fail when Joseph Sheffield gave a huge amount of donation. That really made a huge difference. The school survived and thrived, and they renamed the school as the Chef. So it's a continuing repetitive theme that the college supports science and physics, and the individuals, the faculty, has to find patronage elsewhere if they want to make some significant advances or changes in teaching or research. But anyway, teaching thrived, research was continuing, and we can see some of the courses that were taught at Yale College through the catalog. So again, this is diving into the archives and going through page after page of old documents, trying to make sense of them. So in the college recitations and lectures from 1885, and the reason I don't have anything from 1861 is because I couldn't find them yet. This was the closest I could find. So they have astronomy courses. So this is for freshmen and upper. Geology, oh yeah. So some are for freshmen, and then it's for sophomores, juniors, seniors. They had mechanics and calculus taught by Professor Newton. They had vector analysis, the only course taught by Gibbs. Arthur Wright taught physics, and a course called Graduates, which I presume is research related or new advanced physics topics for graduate students. Optics 1 and 2. So optics was big in 1880s. and also physics and which I presume is mineralogy by E.S. Dana. So these were the physics-related courses in 1885. So there was like specialization. There was robust interest in physics, and physics was an integral part of this liberal education. So who were these students that were taking like these physics science courses? So many of the Yale students came from Connecticut. A lot of them are from New Haven. And the Hopkins School was a preparatory school that prepped students to enter Yale. And the education there was focused on Latin and Greek. And one of the students was Edward Alexander Boucher. And he is remarkable in himself. Like his intellect, his integrity and dedication is amazing and exemplary. If you consider his race, it becomes an even more phenomenal and a very tragic story. So, unfortunately, in the last few years, there's been more and more interest and research done on Boucher. So if you search the internet, there are some like minor contradictions about him, but overall you can find a lot more information about him. So he was born in New Haven in a typically impoverished Black American family, and it's conjectured that his father came from the South as an enslaved person to a rich white man. And it seemed that white man's family sponsored Boucher's education at Hopkins. And he attended Hopkins School from 1868 to 1870. He was valedictorian, so extremely intelligent, hardworking. And he entered Yale in 1870 and was the class of 1874. And he was the only Black person in his class year. He was not the first Black student to attend Yale, but that's not like, finding the first is nice, but that's not the entire story. It's always like finding out who comes next, who's after him. So before and after, there are not that many Black students at Yale. He graduated college. He just didn't go and get a job, but he continued his study. So he entered the graduate school, the department, in 1874. 2 years later, he earned a 6th PhD in physics in the US and at Yale, of course. And we see this portrait in many places, including one downstairs, which is a replica of the original portrait. And I was curious about this. So the original seemed to be the one that's at Sterling Library. And there's so many contradictory informations on the web about this photo. So the best I could find out was the John Wilkinson got to know about, so he was a Yale secretary in the late 70s, 80s. And he was a Yale person who was also headmaster at Hopkins School before he came back to Yale. And it seems he got to know about Boucher when he was at Hopkins. So when he came back to Yale, he commissioned a portrait of Boucher. And an artist, Rudolf Zallinger, he's the one who painted the Age of Reptiles, Age of Mammals at Peabody. He agreed to paint a portrait of Boucher based on this photograph. And the original painting was eventually moved to the location we see in the Sterling Library, maybe in 1990, maybe before, maybe slightly after.
Before you go on, can I just ask, you say he's the 6th PhD in physics in the US, which I've always heard, and Yale, meaning the first 6 were all from Yale?
Yeah.
Okay.
The second place to grant a PhD in physics, I might be wrong, I think it's Johns Hopkins, and that was formed in 1880 something, or late 1870s. So at this time, Yale was still the only place. So Boucher was studying, he was interested in science. And we can get information about who his teachers were from a writing he did for the biographical record for the Yale alumni. So it says, in the fall of 1874, I entered the postgraduate department and so on, and he took experimental physics under Professor Wright, calculus with Professor Newton, chemistry and mineralogy in Sheffield under Professors Allen and Brush. So it also means that, contrary to the popular saying that Yale College and Sheff were like worlds apart, there was actually collaboration and cross-course taking that was taking place. He also lists his hobbies, walking and rowing. He also mentions his classmate, so George Dickerman, Henry Farnham, George Fox, and so on. So that gives a glimpse of who Boucher's classmates were, who his professors were. And this was a very helpful piece of information because I would have loved to see some syllabus or curriculum of what courses people like Gibbs and Wright taught. And they aren't any found officially. But what I did find was in the paper of Arthur Wright, he has manuscripts, drafts written for his articles on meteorites or zodiacal light. And some of them were done on scrap paper. And that scrap paper was students' assignment. So I'm conjecturing what happened was he gave assignments or take-home exams or in-class exams to his students. The students wrote, he handed it in, and it was one side. So he used the other side as the scrap paper to write his draft. So I flipped it, and I was able to find some homework and assignments. And one of them was by George Fox, who was Boucher's friend and classmate. So I can conjecture that. So I couldn't find anything about Boucher. And some names I could identify the class year, some names I couldn't find. So it's still a work in progress. So his friend, George Fox, had to describe something called a Daniell cell, which I never heard of, so I had to search Wikipedia. Anyway, so Fox is describing what a Daniell cell is. So it says the Daniell battery consists of a glass vessel containing a solution of sulfate of copper. And when a voltaic circuit is closed, a current and extra current is formed in opposite direction to the principal current, and when it is opened, a direct current is formed. It doesn't really make much grammatical sense. So my guess was Fox was writing this under stress and pressure, so maybe this was an in-class exam. But they had to learn about Daniell cells in physics class. And another assignment, this is by another person, Richardson, who I couldn't identify which class he was in, but it was in the same pile. So he had to write about currents and resistance. So it's electricity and magnetism we learn in class today. It's highly similar. And another assignment Richardson did, and Richardson seemed to be a very good student because his answers were pretty concise. He writes about, and he solved the question on refractive indices. Maybe I should have written them. So it's the angle of where light enters and where light exits. So it's very similar to what we do in general physics class exercise today. And Boucher must have worked on this because Boucher's PhD thesis was titled on measuring refracting indices. And by the way, there's a conflict on what his thesis title is. So we don't have his thesis. It's lost somewhere. Hopefully it's lost in the archive, so maybe one day it will be found. Some sources say his thesis title is on measuring refracting indices. Others say refractive indices. The physics doesn't matter, but it will also be nice to get the precise name. So he worked on optics in grad school. And the mural painted by Kwado Adaye, which is in the Dixwell neighborhood, just a few blocks away, precisely shows that of how light goes into the spectrum. So that was one way to glean what kind of courses students took in the 1800s by, looking at faculty's scrap paper. So during this time, Boucher was working in the old laboratory that's currently demolished, and the place became too small, and the faculty sought larger place for research and studying. So eventually this place got torn down, and the physics people were able to move to a new place. And we can remember where the old laboratory is thanks to Boucher, because in 2016, the American Physical Society's historic physics site designated, this place got designated as an historic site where Boucher carried out his research. So the plaque is visible on the old campus, Vanderbilt Hall, in the northwest corner. You can go and look at this and take pictures and say, okay, this is where the old laboratory was, and where physics faculty and students in the 1800s worked and studied at. So the Yale College supported physics, but they were not willing to give money to build a new building. So what Arthur Wright did was use his personal connection. And he was friendly with Henry and Thomas Sloan, who agreed to donate money to build a new building. So a new building dedicated to physics was opened here, and it was called the Sloan Laboratory. And I believe it was the first large building that was built purposely to house a science department. And so that's Sloan. And Kent Laboratory, which was chemistry, was created years later, after Sloan. So this became the place where the physics department faculty and students gave lectures and carried out their research. But this was not the only place, because there was Sheffield Scientific School. So this wasn't a place dedicated to physics only. So this was a scientific school where there were other fields of science also being taught and researched on. So this is in today's SSS, across from the Commons, Wolsey Hall. So the Sheffield Scientific School had their own set of buildings, but there was communication and interaction going on between the two. So what was going on at the Sloan Laboratory down campus? So one of the researches that was interesting was X-rays in the late 1800s. So in 1890, end of 1895, beginning of 1896, when William Röntgen published his result on X-rays, Arthur Wright was one of the first people to jump at to reproduce the results. And it's believed that his, the photograph he took here was probably the first photograph, like X-ray photograph taken in North America. But Wright didn't believe Röntgen's interpretation that these were new rays. He thought these were another form of cathode rays, so charged particles. So he extended the interpretation of the old school. Instead of saying that, oh, this is a new phenomena, this is cool, it's like, no, this is a continuation of what we have always seen with cathode ray tubes. But his research was considered super interesting, and whatever the interpretation, Wright and other people, there was another group at Harvard who also took X-ray photographs. They immediately recognized like the medical benefits X-rays can bring. So he gave a lecture reluctantly in February in the old Sloan Laboratory. So we can imagine here, oops, oh no. So somewhere in this building, he gave a lecture. And the lecture was very popular that even though they did not announce it, students and professors were pouring in. And at the end, they closed the door, and then students were scaling the walls and climbing in through the windows. So newspaper articles are not the most trustworthy source. You can't believe what they write word by word. And in my research, I did come across like falsified reports, exaggerations, or underreporting. And it's what we see in today's newspapers. So we do have to take it with a grain of salt. But it seemed like, so I'm not sure if gray-haired professors were willing to trample on the professor who was guarding the door. Maybe that's an exaggeration. But it's undoubtedly, it was a very popular lecture. And what's also remarkable is Wright believed that these rays were cathode rays. However, he did not prevent others from forming their own interpretation. He encouraged younger students or younger instructors like Henry Bumstead to investigate this phenomena. So I found that was pretty remarkable. And another giant figure in physics that I didn't mention that much, Josiah Gibbs, he was steeped in thermodynamics, statistical mechanics. He was not interested in investigating X-rays, but he did not dismiss it. He said, okay, I'm not going to investigate X-rays, but that's me, and others like you, younger generation, you're welcome to investigate it. And I found that gesture was also significant because if one is a very prominent scientist, their viewpoints have a lot of weight on what the younger generation, junior faculties can do. So even though he was not interested in it, he didn't actively participate. But again, I mean, he passively encouraged people to explore new phenomena. So the old Sloan Laboratory was opened in 1883, but not even 30 years passed when Yale, the physics faculty, found that they lacked space again. So that's another testimony of how robust physics research and teaching was going on. And at this point, Wright was going to retire, but he still had connections with the Sloan. So he acted as a conduit, and other faculties also jumped in to find patrons. So the Sloan brothers were not the sole, but they were still donating significant amount of money to build this current building. So the Sloan Physics Laboratory opened in 1912, and it was the first building on Science Hill. So this was initially private property that was donated to Yale. And the first building, a few years later, chemistry also jumped to this place, and they built the Stirling chemistry lab across the street. So we have the Sloan Physics Laboratory here. So one can imagine a very crowded building in the center of campus. That would have given a lot more interaction. And then they got this huge, nice building that was a bit far away from campus. I mean, even today, there's a bit of like a, especially for undergrads, it's a bit of a trek to come up here. So one can imagine how isolating it must have been while liberating with so much space at the same time. One other interesting feature that Meg pointed out was this very room. And again, we go back to the theme of getting more comfortable chairs and desks. So this is a picture I grabbed from the Yale Physics Department newsletters, and Meg pointed out that these were pipes that were connected to the heating system. So it would heat the seats in winter. And it also made an awful lot of noise, apparently. So this was a feature, and it must have been like really nice, like if this was like made in 1912. So again, we see constant like improvements being made. So what goes on in 1900s really build up on the 1800s. So there's a continuum of old physics as well as expansion in teaching and research. And Yale physics clearly benefited from the senior faculty's fame. Arthur Wright was famous. Josiah Gibbs was even more famous. So he was not well known amongst the Yale undergrads, but his fame increased the further away you went from Yale. And many prominent scientists around the world wanted to visit Yale to meet Gibbs. So when J.J. Thomson visited Yale to give the inaugural Silliman lecture, and later when Ernest Lawrence visited Yale a few years later, they wanted to talk with Gibbs. Well, Ernest Lawrence came too late. Gibbs passed away. But they were clearly attracted by the big names. And that had a build-on effect. So it attracted visitors and new faculties. It helped to expand fields of research. In the war years, the fortunes of the department dipped and expanded as expected. The war drew away faculty from the research and teaching. They were, most of the Yale faculties in the First World War would act as consultants to the Navy in New London. During the Second World War, many were participating in the radar project at the RAD lab at MIT. So that drew away people from the department to do teaching and research, but that also brought in new funding. So especially after the Second World War, there were new sources of funding coming from the government, from Office of Naval Research, Atomic Energy Commission, and National Science Foundation. So even before the Second World War, there was continuous development in new fields of physics. So one obvious place is subatomic physics, particle and nuclear physics. So when Ernest Lawrence, who followed his advisor, Swan, to Yale, and then left after being an instructor here for a few years, built the cyclotron at Berkeley. Yale also built, the Yale faculty also built a cyclotron, and it was running in the Sloan Physics Lab basement for years. So that was, we can't say it's the start of subatomic particles because I think it should go back to X-rays, and it continued to build on. But this was one of the first, this was one of the first, where am I? Back. One of the first accelerators, and that continued on and on. So after the Second World War, we see Yale following the national trend where physics was the department that experienced the biggest expansion due to GI Bill, funding, and popularity. Okay, so I'm going to really rush. So these are the Quonset huts that housed the soldiers during the wartime, and we see the Gibbs building, and we don't see the Wright Nuclear Structure Lab yet. It's 1950s, so it's being built. We see the Sloan SPL here. The Wright Nuclear Structure Lab was built and dedicated in 1966. So this again is a testament to the war effort and how physics became prominent, especially particle and nuclear physics. And this was funded by the ONR, Atomic Energy Commission, later Department of Energy, and NSF combined. And there was also a teaching that changed gradually. So as you all know, Yale was undergraduates, was only for male until the late 1960s. So Peter Parker, when he came to Yale in 1966 to teach, he had no women students for it in his undergraduate class. So this is a copy of his syllabus, and it's the introduction to the students. So as far as the conduct of this course is concerned, let me say from the outset that I shall assume that you gentlemen are enrolled in this course as students. Let's face it, you're big boys now. And in this course, as in any courses, you will get out of it just what you put into it. On the other hand, anytime you have a real question of problem, you should always feel free to come see me. So yes, there's the gender dimension of students. It took years of effort from many people to change this and increase the number of women undergraduate majors in Yale physics. We also see the care shown by the faculty, that they should always feel free to come and talk to the faculty. So yes, we do see expansions, increasing diversification of research fields in the courses we teach and the outreach activities we do, as well as the demographics of who's doing physics, who's participating in physics learning, physics research, physics outreach. So maybe in a few years, we will really have a wonderful building in Upper Science Hill when this construction will be done. Okay, so to summarize, the trajectory of Yale physics showcases how American science and physics developed. So I think it's really a very special place to study. And what we see is not sudden jumps, but it's a continuous negotiation, sorry about the typo, with the university administration. It's finding patrons, it's reacting to the socioeconomic surroundings. And change has many time scales, and it takes many participants. Yale physics today is one of the more diverse departments in the US. And this didn't come about all of a sudden overnight. And it wasn't one person who brought it about. It was really a combined work of people in positions of power who chose to act in a certain way. It was also the work of people who were not in positions of power who chose to speak out and who continued the daily work to bring about change in small increments. So I found it was incredibly gratifying and also humbling, and it really brought perspective to me to study what was happening in this place. And also at Sloan Physics Laboratory, I thought this place was always populated, full of research, full of teaching. And it turned out it wasn't so. The place was empty for a while. And it was the decision of some people who decided to bring back research to this building. Yeah. So more about history of physics in this department. So there will be a project that showcases the timeline of WNSL and Wright Lab. And we also have a timeline for the physics of Yale that will be featured in the Sloan Physics Lab first floor. And lastly, I do want to thank again the members of the physics department who generously shared their experiences and their thoughts with me. And I do want to mention 3 books in particular that guided me. So I didn't create all of these. I benefited so much from prior research and from the knowledge of some of you in this audience. So, thank you. I would love to write a book. So at the moment, I'm focusing on writing series of articles. So I want to have a photo essay of the accelerator upgrade that happened at WNSL. I am drafting a scholarly article, as we call it in history, about the history of physics at Yale. So that will be equivalent to like a PhD article in physics.
Yeah, I'm just curious if you're like looking at an old newspaper article and you're thinking, that's probably a little bit made up or exaggerated. How do you like corroborate what is in there? How do you kind of determine what is real?
Yeah, that's so hard. And it's really case by case, and it's reading things over and over again to get a feel for the landscape. And for newspaper articles, it's trying to see if I can find corresponding events or cases in people's letters or other official reports. So it's, so one example I have is for my research on Mount Wilson Observatory. The newspapers were very, they showed a lot of racism towards the Japanese immigrant workers. So I went back to the correspondences and the official report given to the Carnegie Institution of Washington to cross-check, did this really happen? Actually, many things turned out to be blatant exaggerations. But in that case, I had official sources to cross-check. For the case of Yale physics, there's so much information in the archives. I think it's a matter of time to really cross-check what happened when Arthur Wright gave his lecture. Did people really get trampled on? Did people really climb through windows? Yes.
This is a little bit before my time, but I seem to remember it used to be the case as a graduate student that you had to take you had to prove proficiency in foreign language like German or French or Russian. Did you ever encounter either any correspondence between scientists or with journals that was written in these languages that you had to then translate?
For me, okay, so you mean the foreign language requirements for the history or for physics?
Oh, for
history. For physics? Oh, so in the 1800s, a lot of correspondences were done in German. I didn't come across German correspondences here because I didn't, first of all, Arthur Wright didn't have any German correspondences. I didn't pay a huge amount of attention to the Gibbs collection yet, but he was proficient. He was able to communicate in German. In other scientist sources, especially in the late 1800s, early 1900s, they are some correspondences are written in German, and for some American professors who couldn't read or communicate in German, they would ask colleagues to translate for them. And for me, I don't speak German, so when that comes, I would painstakingly transcribe that and have to translate word by word, and then ask someone who's proficient in German to double check my translation. Yeah, right.
I found it interesting that X-ray and spectroscopy were prominent fields, and I feel like that still persists in chemistry. That so I was wondering if you could see some trend in some of the fields persisting or being popular at Yale versus some other fields.
I think you can make that case. So yeah, we can say that. And there was Henry Bumstead. There was also Bertram Boltwood, who was a physical chemist who was also actively involved in X-rays and radioactivity, and that led to what's going on in today's chemistry. I mean, it's not all of what's going on, but that had a profound impact on how chemistry developed at Yale. So it's that double-edged sword. So some happenings do have a profound impact, the various accelerators that were developed at Yale from the 1950s onward. That had an impact on nuclear physics here. But at that point, we would have to link that with what was going on nationally. So yeah, I can't give a full answer. I think it's one component, and it's complicated.
You also mentioned people were willing to invite new fields.
Yeah. Okay. Thank you. And may I repeat that I would love to talk more and learn more from you all. If you have any leads, comments, or information about Yale physics, I would love to hear them.